So today we start with universal gates. One last question you may get, that is define universal gates, or what are universal gates? One question. And one type question, that is one more type question, that is name the universal gates. These two are based on the title. The gate which is used to design all the basic logic gates is called as universal gate. The basic logic gates and or not can be designed by using a gate. Then that gate is called as universal gate. There are two universal gates, that is NAND gate and NOR gates are called as universal gates. It means NAND and NOR are universal gates. So after knowing the 1 mark questions, now we check out the 3 mark questions based on these gates. It is one commonly asked question in the papers is realize NAND gate to AND or NOT gates. It means using NAND gate you can design the basic logic gates. One question, or else you may get one more question, that is realize NOR to AND or NOT gates. It means by using universal gates, right, you can realize that they are called as universal gates, so that by taking one universal gate you can design the 3 basic logic gates. Now we'll start with the first one, that is by using NAND gate. We will realize NAND gate as a universal gate. By using NAND gate, we can design the basic logic gates called as NOT gate, AND gate, and OR gate. Now, first we'll start with the NAND gate can be designed as NOT gate. It means NAND works like NOT. That you can see it here now. See. See here. Already we know the logic symbols of all the gates. So this is nothing but the NAND gate. Right? This is NAND gate logic symbol. But in the basic things, NAND gate has 2 or more inputs, right? But if you observe here input side, we are given only one input, that is one common input. We are given 2 inputs, but both the inputs are same, that is one common input X. Then what may be the output? Output what we'll get is X complement. It means if X is the input, then X bar or X complement will be the output. Means this is acting like, or this is working like NOT gate, because we know that NOT is a inverter. It complements the given inputs. This NAND is also doing the same thing here. By using one common input, that is X, the output will be X complement. See here, algebraically we have shown it here. NOT X, right? NOT X equal to X NAND X. These two are the 2 common inputs we are given. X NAND X. X NAND X is nothing but X complement. You will get output X complement. X dot X whole complement is the output you will get. But by De Morgan's theorem, second theorem, we know that X dot X complement is nothing but X complement plus X complement. By De Morgan's second theorem, we can write that X complement plus X complement can be written as X complement by De Morgan's second theorem. It means by taking X as the common input, we are getting X complement as the output. It means the NAND gate is working like NOT gate. This is one. Then next, We realize that. Next we'll realize the NAND to AND logic gates. NAND gate works like AND gate. That we'll see now. See. To do that, keep it in mind that NAND to, if you want to realize AND or NOT basic logic gates, first thing, what is NAND? We know that NAND is a combination of NOT and AND gate, right? NOT and combination becomes NAND. Always you have to start with the first NOT. By taking one NAND logic symbol, you can prove that it works like NOT gate. NOT N is over from the NAND. Now you can take remaining part. N is over, NOT is over, then AND is remaining. That you can take it as now the NAND works like AND. For that, what we need is two NAND gate symbols. Two NAND gate symbols. Using that, we can design the NAND works like AND gate. See here, first one, first NAND gate. The common NAND gate you have taken. In this, X and Y are the two inputs. Then output, we are familiar now. The complement of the inputs, that is X dot Y, whole complement will be the output. If this X dot Y whole complement is common input for another NAND gate, the output of the first NAND gate is common input for the second NAND gate, then what you will get is X dot Y whole complement into X dot Y whole complement. Right? So that is nothing but finally what we are writing is, after simplification, what you will get is X dot Y by De Morgan's theorem. Is it clear? Now you can see algebraically what we have stated that. See here. See. X and Y are the two inputs. X and Y are the two inputs for NAND gate. At that time, that becomes X NAND Y. NAND X NAND Y. Right? Then proof. X NAND Y equal to what we are getting from the first NAND gate, X dot Y whole complement we will get. If you apply De Morgan's theorem for this, second theorem for this, what you will get is X complement plus Y complement into X NAND Y, NAND X NAND Y will get. Then if you simplify that, X complement plus Y complement, one bracket, then NAND X complement plus Y complement, another bracket. It means these two are common inputs for another NAND gate. At that time what will get? Again X complement plus Y complement into X complement plus Y complement, whole complement you will get. By second theorem, this can be written. Now, by De Morgan's first theorem, right, the OR becomes AND. So, X complement, we are expanding now. We are opening the brackets. X complement and this one complement. X double complement plus becomes dot Y double complement. X double complement into Y double complement. Then dot becomes plus X double complement into Y double complement by De Morgan's first theorem. This we are written. Then we know that by the theorems, Boolean theorems, X double complement is nothing but X, Y double complement is nothing but Y. Based on that theorem, you can write X double complement becomes X into Y double complement becomes Y plus same X dot Y. Then by the theorem X plus X equal to X, by this theorem we can write this X dot Y plus X dot Y is nothing but X dot Y, that is XY. It means if X and Y are the two inputs given for the NAND gate, then the output what we will get is X dot Y. It means the product of these two inputs will get. It means using NAND gate, we have shown that the NAND gate works like AND gate. This is second one. Now, from the NAND Already we have proved not is over, then remaining and is over. Complete NAND is over. Now what is remaining? OR is remaining. We have to show that NAND, using NAND you can design OR gate, right? For that what we need is 3 NAND logic symbols. The sequence is easy. 1 logic symbol, 1 NAND symbol, 2 NAND symbols and 3 NAND logic symbols. 1 is used for NOT, 2 symbols are used for and for OR. Because from the NAND, NOT is over, AND is over, what is remaining is OR. For that what we need is 3 NAND logic symbols are required. So that we have drawn it here. See, we designed. You can take the common input 2 NAND gates. For first NAND gate, X is common. For second NAND gate, Y is common. We know that if X is common for the NAND gate means the output will be X dot Y, X dot X, whole complement will get. If Y is input for this NAND gate means the output what will get is Y dot Y, whole complement will get. Then output will be X plus Y. Here also you can put 1 bubble here. It is missing. Bubble is missing. You can put that. Right? You can draw here 1 bubble. Bubble is required here. Right? You can draw 1 bubble there. Right? Light will get. This also the NAND symbol. Right? A bubble is required here. 1 bubble. Right? That becomes X plus Y. You can see here the algebraic expression how we evaluated that. See, X plus Y is equal to X NAND X NAND Y NAND Y, because X and Y are 2 common inputs for 2 NAND gates. Then X NAND X means X dot X whole complement. If you use De Morgan's second theorem, then that becomes X complement plus X complement. By the theorem of X plus X equal to X, we can write X complement plus X complement is nothing but X complement. In the same way, for the second one, similarly, Y NAND Y becomes Y complement. Now you can go for the third NAND logic symbol. The output of these two, X complement and Y complement, are input for the third NAND gate. Then the expression becomes X NAND X NAND Y is equal to X complement NAND Y complement you will get. So if you perform the NAND operation, then that becomes X complement dot Y complement whole complement you will get. Then by theorem, by De Morgan's theorem, if you write this like this also, that is X 1 complement, 2 complement, X double complement, the dot is changing to plus, then Y complement and complement becomes Y complement by De Morgan's theorem. By first theorem, this can be written like this: X complement dot Y complement whole complement equal to X double complement plus Y double complements. Then we know the theorem: X double complement is nothing but X and Y double complement is nothing but Y. So based on this, you can write that X double complement is X plus Y double complement is Y. The output order we are getting is X plus Y. If X and Y are the inputs for 2 NAND gates, then in the third NAND gate, if you are getting X plus Y is the output, then the NAND gate is working like OR gate. That we have realized here. It means using NAND gate, we have realized that using NAND gate, you can design NOT gate, AND gate, and OR gates, right? So this is of 3 marks question. For exam point of view, it is important. Then next, after that, the NAND-to-NAND logic is best suited for Boolean expression in sum of products form. In SOP form, NAND-to-NAND is the best suited gate for evaluating the expression. That you can check it out here, how best you can do that. See, NAND-to-NAND. You have to follow some rules for NAND-to-NAND logic networks. Design rule for NAND-to-NAND logic networks. Only for two-level circuits it is useful. That is, first rule you have to follow, that is derive simplified sum of products expression. First you have to derive the SOP expression. Then draw a circuit diagram using basic logic gates, that is AND, OR and NOT gates for that particular SOP expression. Then just you can replace the AND or NOT gates with NAND gate. That becomes NAND-to-NAND logic network. For example, X, Y, Z complement plus X complement Z can be drawn as follows. This is one SOP expression we have taken. For this expression, you can draw it now. So first what you can do, you can use basic logic gates and draw the circuit diagram. Then you can just replace all the basic logic gates with the NAND gate. That becomes NAND-to-NAND logic network. Now see here, X, Y, Z complement is there. So you have taken the X into Y into Z complement it is. That's why you are taking AND gate, because AND is a logical and performs logical multiplication operation. So that's why I have taken this gate. Then we are assuming that the complement is direct, right? Inputs there, complements are available for us. Based on that, we have taken. So X, Y, Z complement are 3 inputs for this AND gate, right? One AND gate. Then this is over. First operand. Second operand you can check out. X complement Z. X complement into Z it is. So again we need AND gate. We have taken one more AND gate. Then we have given input as X complement and Z. Then after designing these two operands, then in between there is a plus is there. Plus means we know that OR gate performs logical addition. So the output of these two AND gate will be the input for OR gate. The output of first AND gate, output of second AND gate will be the input for the OR gate. Then the result will be X, Y, Z complement plus X complement Z. So we have designed using AND or NOT gate, basic logic gates. Now our task is to get NAND-to-NAND logic network. So just what you can do is you can replace AND gate and OR gate with NAND gates here. The AND is replaced with NAND, this AND is replaced with NAND, then this OR is replaced with another NAND, then this is the NAND-to-NAND logic network. I hope you cleared this. You understood that. Now next, one more example we will take. Draw the diagram of a digital circuit for the function. That is, function is given. For this we have to design a digital circuit. Draw a digital circuit. You have to design f of x, y, z. It means 3 inputs are there here. Is equal to 3 variable, it is yz plus xz. Yz plus xz using NAND gate only. Using NAND gate, you can design a circuit for this given function. Then the solution, f of xyz equal to yz plus xz. This is given. Can be written as, this can be written as, see here, the RHS side, LHS is same, f of xyz equal to, yz means y NAND z, because using NAND gate they are given. So y NAND Z. Then this is there NAND, right? NAND. Then X NAND Z. The given expression can be rewritten like this. Now you can design a circuit diagram for the given expression. That is, see here, first, Y NAND Z is there. Y and Z are the two inputs for this first NAND gate. This over. Now, second one, this again X NAND Z. One more NAND gate are taken. For that, two inputs are X and Z, two inputs. Then, first NAND gate output what will get is Y dot Z whole complement will get, and the second NAND gate output we are getting it as X dot Z whole complement. The output of these two NAND gates are input for the third NAND gate. Then the output what will get is YZ plus XZ. This is one more example. Now we'll check out one more example, next example. See here, draw the diagram of digital circuit f of ABC equal to AB plus BC plus CD using NAND to NAND logic. Using NAND to NAND, not only NAND, using NAND to NAND logic you have to use, and draw the diagram for this given expression. So f of ABC is equal to AB plus BC plus CD. Now you can rewrite that using NAND. So A NAND B, this first operand is completed. A NAND B, NAND, B NAND C, NAND, C NAND D. It means again we are using three NAND gates that you can see it here. See, three NAND gates are there. Right? So first NAND gate, A and B are the inputs. The output will be A dot B whole complement. And second NAND gate, P and C are the inputs. The output will be B dot C whole complement. And third NAND gate, CD is there, so output will be C dot D whole complement. If these three output will be input for the fourth NAND gate, then what you'll get is the given expression AB plus BC plus CD, because A dot B complement becomes double complement, AB will get, B dot C complement becomes double complement, so BC will get, then C dot D whole complement becomes double complement, so that will be CD. This is the required output will get. Then next, see next one, draw the circuit diagram for f of A B complement C plus C complement B using NAND to NAND logic only. NAND to NAND logic network you can use, and you can draw the circuit diagram for that. You can see the answers here. F of B complement C plus C complement B can be written as, in a NAND to NAND logic circuit, A NAND of not B. NAND C. See here, A NAND of not B, because complement is there, not B. NAND C. This first operand is over. Then plus means NAND C complement B, you write not C NAND B for C complement B. Then once you are capable of writing this, means you can easily design the circuit here. See, first one, A is input for NAND gate, fine. Then not B is there. Using NAND only you write. That's why NAND gate common input is B. Then what you will get is B complement. You should not use not basic logic gate here. Using NAND only. That's you have to concentrate here. If you put here not symbol, basic logic gate, then your circuit diagram will be wrong. You can keep it in mind that this is NAND to NAND logic network we are following. Clearly it is mentioned here, NAND to NAND logic only. You should not use any other gates, right? So B is common input for one NAND gate, then output will be complement. Then C. These three are the input, then output what will get is A, B complement, C will be the output will get. Right? Then next one, C complement B is the input for another NAND gate. Again, you have to follow the same method. C you can take, give input for a common input for one NAND gate, then what we'll get is C complement and B. C complement B, right, is the input for this gate. Then the final output, the output of these two NAND gates are input for the third NAND gate, then the output will be A, B complement C plus C complement B. So this is all about the NAND gates. In this, what we have studied is, one, we have realized, right? Realize NAND gate works like NOT and OR gate. This is one part that is very important for exam point of view. Then one more part we have completed related to that using NAND is NAND to NAND logic network. In that, only using NAND gate you can design the logic circuits. Then next, one more important 3 marks question what we'll get is, that is just like NAND, now you can go with NOR. NOR, realize NOR gate, right, works like AND gate, OR gate and NOT gate. Again, you have to realize that. Now, the first part, we are realizing that NOR to NOT logic. NOR, using NOR, you can design the NOT, right? So in the NOR, again, if you observe, NOR is a combination of NOT and OR. So first you can take it as NOT, so NOT. So NOT purpose, again, we are taking the NOR logic symbol, one NOR logic symbol. For that, one input is common because we are proving this works like NOT gate. So one common input A, then output will be A complement. See here, NOT X, right, equal to X NOR X. See here, instead of A, you can write it as, you have taken it as X here. So if X is the common input for this NOR gate, then X complement will be the output. So that we are taking it here, X NOR X. So that is nothing but the output what we'll get is X plus X whole complement. X plus X whole complement will get, because NOR is complement of OR. NOR is a complement of OR. So output what we are getting is X plus X whole complement. By De Morgan's theorem, this can be written as X complement into X complement. By theorem, X plus X equal to X. By that theorem, you can write X complement dot X complement can be written as X complement. That is X complement dot X complement is nothing but X complement by theorem. X dot X equal to X. By that theorem, by using that theorem, this can be written as X complement. It means if X is the common input for the NOR gate, the output will be X complement. It means the NOR gate is working like NOT gate that we have proved here. First one. Then next. Second, from the NOR, NOT is over. What is remaining is OR. See the logic, you have to follow this. Otherwise, you will confuse yourself and you will draw the wrong things. In the NAND also stated. In the NAND, first you have taken NOT, then remaining AND you have taken, then lastly you went with OR. Here the same strategy I am following. From the NOR, first I have taken NOT, now we are taking OR. It means again to design NOR to OR, we need two NOR gates. Using two NOR logic symbols, we can design NOR to OR operation. So first one, first NOR logic symbol, if A and B are the input for that, then output will be A plus B whole complement. If this output of this A plus B whole complement is input for another NOR gate, there is a common input for another NOR gate, then what we'll get is A plus B. It means by using two logic NOR symbols, we are designing that NOR to OR. Right? Then third one. Same what you stated in the NAND case, same thing you're taking. Now, from the NOR, NOT is over, OR is over, what is remaining is AND. So lastly we are going with NOR to AND operation. NOR to AND. So A dot B equal to A nor B nor B. See, we are using 3 NOR logic symbols to prove that NOR to AND. NOR works like AND. Are using NOR, you can design AND gate by using 3 logic symbols. So first logic symbol, first NOR gate contains common input as A, then output will be A complement. And second NOR gate contains B as a common input, so output will be B complement. If these two, A complement and B complement, are the input for the third NOR gate, then the output will be A dot B by De Morgan's theorem. Right? So it means in the today's class, we have completed a set of questions, a set of questions, that is realize NAND to AND or not, and realize NOR to AND or not. Along with that, we have completed one more, that is the NAND to NAND logic network. So from this, the questions may be expected for the exams, right? So if you find any difficulty, just post your doubts so that you'll get the solutions for that, right? So thank you.